Welcome to our presentation. Our work is about to do shape completion, a reconstruction from a single depth map. As you can see, the input depth map can unproject to a surface point cloud, and our goal is to predict the missing points on the object's surface. However, since the input image is only a partial scan of the object, and more than 50% of the information is missing. So how to predict the missing information? Maybe we can start with the input point cloud, the first and intuitive way we call information enhancement. This is based on the observation that most man-made objects are symmetrical. For example, the yellow plane of sofa. If we mirror the input point cloud through this yellow plane, the missing points on the right side will be completed by the left side points. This idea is utilized in the work of Wang et al. However, this way requires known symmetry planes, which is in fact a rather strict condition. Thus we have to predict a symmetry plane from the incomplete point cloud of objects. However, it is not good enough to directly and explicitly mirror the input point cloud. An inaccurate symmetry plane will make the mirrored point cloud become hierarchical, which in turn adds a lot of error. Also, there are still many asymmetrical objects in the world. The second way of utilizing the input point cloud we call reuse of information. By projecting the input point cloud under some nearby camera viewpoints, we can get some incomplete depth maps. If we could inpaint these projected depth maps, then these maps can be unprojected and merged into a complete point cloud. So how can we pick these viewpoints? One idea is that we just choose the opposite viewpoint of the input map and do image inpainting on this back view image. Yao et al. Adopted this idea in their CVPR 2020's work, but since the front and back viewpoints can't cover the whole object very well, some surfaces will be missing. If the back view doesn't work, then is it possible to predefine some fixed viewpoints? Unfortunately, for different object classes and camera poses, the inpainting performance at the same projection viewpoint will vary significantly. For the problem of error increasing caused by directly utilizing the predicted symmetry plane for point cloud mirroring, we implicitly utilize the symmetry information by aligning the point cloud with the symmetry plane and jointly inpainting the depth maps under the symmetric viewpoints. And we use a reinforcement learning agent to autonomously select the optimal sequence of inpainting viewpoints. We also added the loop in our method because more complete shapes contribute to more robust symmetry plane estimates and vice versa. The input of our proposed method is a depth map of an object, and it can be unprojected to a surface point cloud. We first predict its symmetry plane and align the point cloud by the predicted symmetry. Then the aligned point cloud will be fed into the viewpoint selection module to seek the best next view for depth map inpainting. Actually, the output viewpoint is defined by elevation angle theta and azimuth angle phi. For initial point cloud P0, the viewpoint selection module outputs symmetric viewpoints V0 and V'0. Projecting P0 in the above viewpoints, we get the depth maps D0 and D'0. Inpainting these depth maps through the 2D inpainting module, we obtain the complete depth maps D'0, D'0. The inpainting module consists of three parts: mask generation part, normal inpainting part, and depth inpainting part. Note that we add pairwise skip connections between the two input and output heads for exchanging symmetry information. The inpainted depth maps will be unprojected to point clouds, and these points will fuse P0 to get P1, input P1 to view selection module, and project P1 with viewpoints V1 V'1. We will get depth maps D1 and D'1. Inpainting these two images and repeating the above process, we will get the point cloud P2, P3, P4. We argue that P4 is relatively complete, and therefore reperform the symmetry plane prediction on it to obtain a more accurate result. We reset the point cloud to its initial state and align it with the re-estimated symmetry plane to obtain P'0. Again, after 4 more iterations, re-estimate the symmetry plane for P8. And so it goes until we finally get P20. Combining the above steps in a single graph gives the pipeline of proposed ISC-net. With Poisson surface reconstruction algorithm, the object mesh model is finally reconstructed from the input depth map. Next are some qualitative comparison, first shown on the synthetic dataset, ShapeNet. Next are the results on real scan dataset, ScanNet. To summary, the proposed ISC-net exploits reflective symmetry cues implicitly to obtain more detailed shapes. The shape completion was performed from pairs of viewpoints, reflected across the symmetry plane, predicted by a reinforcement learning agent to improve robustness. Also, ISC-net jointly estimates the symmetry plane and shape completion iteratively. Thank you.